Today we're going to be looking at section 10.6, which is about parametric equations. Our learning targets for this week's lesson are that we can graph a parametric equation, we can eliminate a parameter to write a rectangular equation, and that we can write parametric equations given a rectangular equation and a parameter. Let's start with some definitions. Parametric equations are a set of two or more equations that express quantities in terms of an independent variable that is known as the parameter. Usually that parameter would be time or angle. A plane curve is the path formed by the graph of a parametric equation. And a rectangular equation is the equation that you're used to, an equation written in terms of both x and y. So let's look at example 1. We're going to sketch the plane curve given by the parametric equations x equals t squared minus 6 and y is equal to 3t for values of t that are in between -3 and +3. We're going to make a table, a 3-column table of values. So we need a column for t, a column for x, and a column for y. So if we plug in -3 for t into our equation for x, -3 squared minus 6 is going to give us 3. We plug in -2. -2 squared is 4. 4 minus 6 is -2. When we plug in -1, -1 squared is 1. 1 minus 6 is -5. When we plug in 0, 0 squared minus 6 is -6. We continue for values for 1, 2, and 3. Same thing, we're going to plug these numbers into our equation for y. So if I plug -3 in for y, 3 times -3 is -9. When we plug in -2, 3 times -2 is -6. When we plug in -1, 3 times -1 is -3, and so on. Our next step is going to be to plot the x and y coordinates from the table. So our first point here, when t is -3, our x coordinate is 3, our y coordinate is -9. So we would go to 3, -9. And here's our point, and I've labeled it with a t value. Our next point, x is -2 and y is -6. So -2, -6 when t was -2. We have a point where x is -5 and y is -3 when t is -1. We have a point where x is -6 and y is 0, and that happened when t was 0. We have a point at -5, +3 when t is 1. A point at -2, 6 when t is +2. And we have a point at 3, 9 when t is 3. And then we can connect those points to make our curve. Next up, example 2, we're going to eliminate the parameter from the parametric equations that were given in example 1. To do that, you're going to solve one equation for the parameter, get t by itself, and then you'll substitute that into your second equation and simplify. So our parametric equations were x equals t squared minus 6 and y is equal to 3t. The equation that's easiest to solve for t is going to be the second one here, that y is equal to 3t. If you solve that to get t by itself, you can divide both sides by 3. You're going to get t is equal to y divided by 3. And now if we substitute this into our first equation in place of the t, we'll have x equals the quantity y divided by 3 squared minus 6. And now we're going to simplify this equation. Y squared is y squared, 3 squared is 9. So we have x equals y squared over 9 minus 6. And now recall that this whole chapter has been about conic sections. So you might recognize that this is going to be one of our conic sections. In fact, it's going to be a parabola since there's only one square term. So we want to get it into the standard form for the conic section that this equation represents. So to make that happen, let's add 6 to both sides. So now we have x plus 6 is equal to y squared over 9. And then if we multiply both sides by 9, we get y squared equals 9 times the quantity x plus 6. We can see this is a horizontal parabola. There's only one square term, so we know it's a parabola. And it's horizontal because it's the y that's being squared instead of the x that's being squared. We know our vertex is at -6, 0, right? The opposite of what's in this parentheses. You could write this other side as y minus 0 squared if you wanted to. If you were going to graph this without having made the table that we did in example 1, then you would want to find like your p-value to find your focus and your directrix. We know that 4p is equal to our constant in front of our parentheses. So 4p is equal to 9. P is equal to 9/4, or 2.25. So we know our focus is going to be 9/4, so 2.25 spaces to the right of our vertex. Our directrix would be 2¼ spaces to the left, and you could use that to sketch the graph if you hadn't made the table of values like we did in example 1. Next example, example 3. For part A, we're going to sketch the curve that's represented by the parametric equations, and then for part B, we're going to eliminate the parameter and write the resulting rectangular equation. And even though the directions tell us to do A then B, it's okay if you do part B first and then go back and do part A. If you wanted to do part A first, you'd have to make a table of values, choose some different numbers to put in for theta for the angle, and then if you remembered your unit circle from first semester, you could figure those out, or you could use a calculator. But if we eliminate our parameter first, it's actually going to be much quicker for us to make the graph of this. Okay? So let's start with eliminating the parameter. And in fact, if you recall from first semester, we have an equation that relates sine and cosine. We know the Pythagorean identity, cosine squared plus sine squared is equal to 1. So what we're going to do is take our two parametric equations here, and we're going to use those to isolate the cosine theta and the sine theta in each of those equations. In this equation, if you divide both sides by 2, you're going to get cosine theta equals x/2. From this equation, if you divide both sides by 3, you're going to get sine theta is equal to y divided by 3. And now we can substitute these values into the Pythagorean identity to simplify and obtain our rectangular equation. So notice that this here is cosine squared, cosine times cosine. So I'm going to have x/2 to replace my cosine squared. And then again, we have sine squared. So if we replace sine with y/3, we'll have to square that to get our sine squared is equal to 1. And now just a little tiny bit of simplifying. X squared is x squared, 2 squared is 4, y squared is y squared, 3 squared is 9. So our rectangular equation is x squared over 4 plus y squared over 9 is equal to 1. And hopefully you recognize this as an ellipse, in fact, as a vertical ellipse, because we have a larger number underneath the y squared term. Our center is going to be the point 0, 0. Our a value, since a squared is 9, a is 3, b squared is 4, so b is 2, and we can use this to make our graph. If we put our center at 0, 0, we know we're going 3 spaces above and below that to get to our vertices. So we have a vertex at 0, 3 and a vertex at 0, -3. Since b is 2, we're going to go 2 spaces to the left and to the right to get to our co-vertices. And then once you have those 4 points, you can connect them to make your ellipse. Next up, same idea, but a different set of parametric equations. So we're going to eliminate the parameter, write the rectangular equation, and sketch the curve. This time we have x equals 1 plus 3 times the secant of theta, and y is equal to -3 plus the tangent of theta. And if you recall from first semester, one of our other versions of our Pythagorean identity is that 1 plus tangent squared is equal to secant squared. Or if we want to isolate the 1, if we subtract tangent squared on both sides, we get secant squared minus tangent squared is equal to 1. So same process, we're going to isolate the secant theta and the tangent theta and then substitute those into this alternate version of our Pythagorean identity there. So in this equation, if we subtract 1 and then divide by 3, we're going to get secant theta is equal to x minus 1 over 3. From our second parametric equation, to get tangent theta by itself, you'd have to add 3. So we get tangent theta is equal to y plus 3. And now we can substitute these in for secant theta and tangent theta in our Pythagorean identity. So if we replace secant with x minus 1 over 3 and then square it, minus our tangent, y plus 3, quantity squared is equal to 1. You don't need to multiply out the x minus 1 squared. Just leave it as x minus 1 quantity squared, but 3 squared is 9. Minus y plus 3 squared. Let's go ahead and write that as over 1 just to make it a little bit easier to recognize our conic section and to make our graph for this is equal to 1. Hopefully you recognize that this is a hyperbola. We've got two square terms that are being subtracted. This is a horizontal hyperbola because our x term is positive. Our center would be the point 1 comma negative 3. A squared is 9, so A is 3. B squared is 1, so B is 1. And we can use that information to sketch our curve. So if we put our center at 1, negative 3, it's marked with the C there in green. Then since A is 3 and it's horizontal, we're going 3 spaces to the left and right of our center to get to our vertices. So we have a vertex at negative 2 comma negative 3 and our other vertex at 4 comma negative 3. Since B is 1, we're going to go 1 space above and below our center to get to our co-vertices. So we have a co-vertex at 1, negative 2 and another one at 1, negative 4. Then you can make your guiding rectangle around those 4 points. You can see that here in orange. Draw in your diagonals for your asymptotes there in red. And then finally, you can do your 2 branches of your hyperbola using the asymptotes and the vertices, as you see here in the purple curves. Our last example for today, we're going to find a set of parametric equations to represent the rectangular equation y equals 4 times the quantity x minus 3 squared using each parameter. So for the first one, we're going to use the parameter that t is equal to x. Pardon me. So our goal here is to get an equation for x in terms of t and an equation for y in terms of t, right? That's what our parametric equation is going to look like. Our equation for x was really given to us, right? T is equal to x, that's the same as x is equal to t. And now we can substitute this into our rectangular equation to get an equation of y in terms of t. So y equals 4 times the quantity x minus 3 squared. When I replace x with t, becomes y equals 4 times t minus 3 quantity squared. Now we are going to simplify this completely. So we're going to multiply out t minus 3 squared. If it helps you to make a box, you can. T minus 3 times t minus 3, t times t is t squared. T times negative 3 is negative 3t. Same thing here. And negative 3 times negative 3 is positive 9. So now we have y equals 4 times, when we multiply this out, we've got a t squared, a negative 6t, and a plus 9. And then we can distribute our 4. So then we end up with our parametric equations. Our x equation, x is equal to t. And then our y equation, after we distributed that 4, we get 4t squared minus 24t plus 36. That one's pretty nice because we already had x in terms of t. Sometimes they won't be quite that friendly. So let's look at part B here, when t is equal to 2 minus x. Okay, so our first goal, we have to get x in terms of t. So if I add x to both sides, I would get x plus t is equal to 2. And then to get x all the way by itself, if you subtract t from both sides, we have x is equal to 2 minus t. Once we have x in terms of t, we can substitute this in place of the x in our original rectangular equation. So replacing the x with 2 minus t, now we have y equals 4 times the quantity 2 minus t minus 3 squared. We can simplify 2 minus 3 gives us negative 1, so y equals 4 times negative t minus 1 squared. If we multiply out negative t minus 1 times negative t minus 1 using a box or double distribute, Negative t times negative t is positive t squared. Negative t times negative 1 is positive 1t, same thing here. And negative 1 times negative 1 is positive 1. So we have y equals 4 times t squared. 1t plus 1t gives us 2t and our positive 1. So for our parametric equations, our equation for x was x equals 2 minus t. And our equation for y, after we distribute the 4, we get y equals 4t squared plus 8t plus 4. That's the end of our examples for today. Please let me know if you have any questions. I'd be happy to help you.